Here we are. This problem is not super simple, so let me explain the problem and then I'll tell you what we're going to do. So the idea is that there's a spherical inverted bowl with a piece of ice right on the top. I give it a tiny little nudge. Forgive my fingers, I got some paint on them. And it starts to slide down the bowl. At some point, it loses contact with the bowl. And we want to find out what angle from the starting point does it lose contact. Now, I did this problem before. I actually did it twice. The first time, I used forces and energy to find out when the normal force is equal to 0, and then it's not so bad to solve. That's not too bad of a problem. The other way, I actually did a numerical model where I said that there's a spring force pushing this up, and then just let it go down, and I thought that was pretty cool. I liked it a lot. But traditionally, this problem is given as an example to use Lagrangian and forces of constraint. And so that's what I'm going to do. And the problem's not so bad. It's just there's a trick at the end, and I don't like tricks. But I'm gonna show you the trick, and then I'll show you another way to solve it. So the idea is that in Lagrangian mechanics, we can constrain the motion over a particular path. In this case, you could say it has to stay on the surface of the sphere. And then if I under-constrain it, if I give it an extra variable, I can actually apply a force of constraint, an equation of constraint, and find that force of constraint. And that's what I want to do. I want to find the force of constraint in this case and find out when that goes to 0. When there's no more force pushing this up, that's when it loses contact. So the way we do this is first to define Lagrangian, which is kinetic energy minus potential energy. This is part of the Lagrange equation, and it turns out that this function is minimized. The function that minimizes the action over some time integral is the equation of motion. That's the whole idea behind the Lagrangian. If I have suppose I have variables x and y, which I'm going to use something different, where I have some equation of constraint that relates the values of x and y, and I call that f. Then, using the Euler Lagrange equation with this Lagrange multipliers, I get the following equation. This is just for x. This says that if I take the Lagrangian and the partial of that with respect to x plus some Lagrange multiplier, lambda, times the partial of f with respect to x, f, is equal to the time derivative of the partial of L with respect to the velocity x dot. And so the idea is I need to find this fx is going to be lambda partial of f with respect to x. That's the x constraint force. Okay, so this is really a 1-degree freedom problem because you could just describe this in terms of the angle theta, but I want to under-constrain it so that I can find that constraint force. So in this case, I'm actually going to need two variables. Let's say that it can be some distance r away and some angle theta. Now I need to get the kinetic energy and the potential energy. So to do that, the best thing to do is to get this kinetic energy in terms of x and y. So if I can write the Lagrangian as this: 1/2 m x dot squared plus y dot squared minus the potential, and the potential is going to be mgy, so it's going to be minus mgy. And now I can get expressions for x and y. So let's say x, if I draw that up here, so imagine my mass is right there. This is the variable r. That's the y component and the x component. Sorry, my picture is kind of small. I did this problem a whole bunch of times because I kept making a mistake. So I might accidentally skip some steps, but I also don't want to make an hour-long video, and I'm still talking. Why don't I just shut up and do the problem? Okay, so here is the x-coordinate is this side, the adjacent, so that's going to be r sine theta. The y-coordinate is going to be this side, r cosine theta. Now I need the derivatives, so let's take the derivatives. X dot equals, okay, this is the mistake I made as an undergraduate, and I remember it. I forgot that both of these changed, so I have to use the product rule. So I'm going to say r dot times sine of theta. Now I have to take the derivative of sine theta, so it's going to be plus r times sine, the derivative of sine of theta is cosine theta, and then I have to take the derivative of the inside, and I get theta dot. Now I'm going to do this for y dot, so I get the derivative of r is r dot times cosine theta plus r times the derivative of cosine theta, which is minus sine theta, theta dot. Now I'm going to need to square both of these, so I'm going to get x dot squared. I get So I have two terms. So I'm going to get this times itself. So r dot squared times sine squared theta. Now I'm going to get this term times that plus that times that. So two of these. So I get plus 2. I'm going to move this over here. R dot cosine theta sine theta. And then I have this times itself. So plus, running out of room, r squared, going to make it cosine squared theta dot. Cosine theta r dot theta. Sorry. Plus r squared theta dot squared cosine squared theta. Is that okay? Okay, now I'm going to do the same thing for y. So y dot squared is going to get this term, r dot squared cosine squared theta. Now I'm going to get this times this plus this times that, so I get minus 2r dot theta dot cosine theta sine theta plus this squared, so it's going to be r squared theta dot squared. I move the theta dot over, sine squared theta. Okay, so now I need to get x dot squared plus y dot squared. So let's just do this. So here I have this term plus this term. I can factor out the r dot squared. I get r dot squared times sine squared theta plus cosine squared theta. And sine squared plus cosine squared is 1. Even if you write it terribly messy, it's still 1. Okay, so this is just going to be equal to r dot squared. Here I have this term plus this term, but they're the same except that one's negative, so they cancel. And then here I have sine squared plus cosine squared again, if I can factor out, so I get plus r squared theta dot squared. So now, and then I can put in my value for y, and I get L equals 1/2 m r dot squared plus r squared theta dot squared minus m g r cosine theta. That's my Lagrangian. Okay, now I need my function f. So what is my constraint? I want to constrain the box to be on the surface of the sphere of radius capital R. So I can say r minus r equals 0, and that's going to be f of r theta. Is that okay? Because r equals r, so I just put it as equals 0. That's the way you usually do it. Okay, now we're ready to plug it into this. We're going to get two of these equations. I'm going to do one for r, one for r, and then one for theta. I had my cheat sheet here because I did work this out. Oh well, I'm just gonna wing it. I'm gonna make it work. Arg, I feel anxiety now. Okay, well here's L. 1/2. I put it there because I'm like, I'm gonna make a mistake. I made this mistake a bunch of times, but I'm just recopying this. R dot squared plus r squared theta dot squared minus mg r cosine theta f of r theta equals r minus r equals 0. I'm getting it because I know I'm going to make a mistake. And then I'm going to be really... Here it is. I found it. Okay. Here's my cheat sheet, I think. No. Okay, I'm just going to... You guys are going to have to trust that I can make this work. And here's part of it. Oh, that's the one I just did. Okay, whatever. Just keep going. Okay, so now let's do the theta. So I'll write it out. Partial of L with respect to theta plus lambda partial of F with respect to theta equals d dt partial of L with respect to theta dot. So the partial of L with respect to theta is going to be equal to, looking for thetas. There's the only theta. So I get the derivative of cosine theta is going to be sine theta. So I get mg r sine theta. Partial of F with respect to theta. There's no theta in there, so that's 0. So that whole term goes away. Then I need the partial of L with respect to theta dot. So right here I get 1. So I have bring the power rule. So I'll bring the 2 down. So I have 2 over 2. I have m m r squared theta dot. That's it. Now I need to take the derivative of that. So the derivative with respect to time of partial of L with respect to theta dot. I have 2mr theta dot plus mr, oh wait, it's going to be 2mr r dot theta dot plus m r squared theta double dot, right? Because I take the derivative of this term, I get 2r, then I can take the derivative of r, which is r dot. And then I do it again with this, and the derivative of theta is just theta double dot. There you go. So let's put this together, and I get mg r sine theta equals 2mr r dot theta dot plus mr squared theta double dot. That's good. Okay, now we need to do it for r. Partial of L with respect to r plus lambda partial of f with respect to r equals d dt partial of L with respect to r dot. So I'm going to do these by parts. Partial of L with respect to r. So there's my r. There's an r. So I bring down the power rule. So it's going to be 2 over 2. So it's going to be equal to mr theta dot squared. And then here I have another one, so minus mg cosine theta. Okay, now let's take the partial of f with respect to r. Is this going to be 1, right? So I'm just going to have a lambda there. And then the partial of L with respect to r dot, it's going to be equal to, here's 1, so I get m r dot, and that's the only one. So and then if I take the derivative of that with respect to time, it's just mr double dot. So let's put it together. So I have this term, mr theta dot squared minus mg cosine theta. That's that. Then I have this plus lambda equals mr double dot. Okay. Next, I don't need that. Next, I'm going to apply the constraint. Because here I have r's and thetas in here, but I know the relationship between these right here. So if I take the derivative of this, I get r dot equal, I get following. R equals r dot equals 0, r double dot equals 0, right? Because if I take the derivative of this, then that's a constant. That's a constant. So I get just r dot equals 0. Take the derivative again, I get r double dot is equal to 0. So now I can put those into these equations up here, and I get this one is going to be mg capital R sine theta equals, now this term I have an r dot 0, so that's gone. So I get m r squared theta double dot. Let's go ahead and solve for theta double dot. The mass cancels. If I divide this by r squared, I get theta double dot equals g over r sine theta. Now let's do the same thing down here. I get m r theta dot squared minus mg cosine theta plus lambda equals 0. So let's solve this for theta dot squared. So I get theta dot squared equals mg, oh, the m's going to cancel right there. It's going to be g, if I add that to both sides, I get g over r cosine theta minus lambda over mr. Okay, so we're done except for the trick, okay? Because if you look right here, I have an expression of theta double dot in terms of theta and have an expression of theta dot in terms of theta. So it's not a trivial differential system of differential equations to solve, but they are solvable. So let me just rewrite those two because those are important. Start on a new sheet of paper. What are we doing on time? 14 minutes. Okay. I want to keep it under, I don't know what I want to do. Okay. Theta double dot equals g over r sine theta, theta dot squared equals g over r cosine theta minus lambda over mr. So I can actually take the square root of both sides, and I get theta dot equals g over r cosine theta minus lambda over mr to the 1/2. And there is something here that is going to make this a little bit easier, and that's that I really do in the end want to find when lambda is equal to 0, because the F force is lambda times 1, and so that's that, so it's not so bad. Now I really do want to make sure I find that trick. I'm not even going to pause it. I'm just going to, oh, here it is. Is this it? No. Because I did it, and I don't want to make the same mistake. Got it. Okay, let me just check and make sure I'm doing things right. Okay. No, that's not it. This is it. Okay, I'm still here. Okay. Let's guess. The best way to solve a differential equation is to guess. And I found this online, so, and I'll put the link down below. But let's say I guess that theta dot is equal to a plus b cosine theta to the 1/2. Let's say that's my function. That's my solution, where I don't know a and b. And now let me take the derivative to get an expression here. So I'm going to take the derivative of this. So dt theta dot is going to be equal to, I use the power rule first, bring the 1/2 down, 1/2, and then I have a plus b times cosine theta. And then I reduce this by a power of 1, so I get to the negative 1/2. Now I have to take the derivative of the stuff inside. So the derivative of a is 0, and then the derivative of b cosine theta is going to be negative b sine theta times theta dot. So this is going to be equal to, I'm going to put this on the bottom. I get negative b over 2 sine theta, theta dot, over a plus b cosine theta to the 1/2. So instead of writing it to the minus 1/2 power, move to the bottom. But now I get theta dot is a plus b to the cosine theta to the 1/2. I have that in the bottom too. So this cancels that. So that's also, I get the derivative of theta dot is theta double dot, and that's equal to negative b over 2 sine theta. Just checking here. Okay, but that also has to equal this. That has to equal g over r sine theta, because that's theta double dot. So that means that b is equal to negative 2g over r, if I just solve this for b. Okay, that means now I have theta dot is equal to, up here I know b, so it's a plus b, which is actually minus 2g over r cosine theta to the 1/2. Now let's just think here for a second. At t equals 0, then I have theta is equal to 0, right? Let me go back to my picture up here. At the very top, theta is equal to 0, but I also want to start it from rest. Yes, I'm going to give it a tiny nudge, but let's just say I actually started from rest. So theta, when theta equals 0, theta dot has to be equal to 0. So if I put in 0 right here, then I get theta dot equals 0 equals a minus 2g over r. Cosine of 0 is 1 to the 1/2. So now I can square that. And the only way that works is if a equals 2g over r. Is that right? Checking over my notes here. This is a mess. Yes. Okay. So now I get theta dot, putting these a and b in, I get theta dot equals 2g over r plus minus 2g over r cosine theta, all of that to the 1/2. Okay, so that's my expression for theta dot. Now I can put that in up. Oh my gosh, I'm losing my mind here. There's all the paper. Not there. You guys must hate this video. Okay, I can put that in right here and solve for when lambda is equal to 0. So let's do that. So I want lambda to be equal to 0. So let's just solve this for lambda. Let's just solve for, actually, no. Let's just say if lambda equals 0, then this has to be true. So if lambda equals 0, then theta dot squared equals g over r cosine theta. Okay, I got it. I got it now. Where to put my other paper? So then I just said, here it is. I also said theta dot is this. So if I square that, I get 2g over r minus 2g over r cosine theta equals g over r cosine theta. So I'm going to add this to both sides, and I get 2g over r equals 3g over r cosine theta. So now I can solve for cosine theta. Cosine theta equals 2/3. Theta equals the inverse cosine of 2/3. And I did it. That's the answer. I did the answer before. I did it. I'm so mad because I hate tricks. That's a tricky trick stuff. There is another way, another trick that you can do this. But that's the trick that I understood the best. I'm going to do this a third way. I mean another way. Because look, let's go back over here to this. This expression, these two expressions are good. Now this one and this one. So these are differential equations. If I know the starting conditions, I can say the following. I can say theta double dot equals the derivative over some short time interval. Actually, I can say it's delta theta dot over delta t, which is theta dot 2 minus theta dot 1 over delta t. So if I multiply both sides by delta t and add theta 1, I get theta dot 2 equals theta dot 1 plus theta double dot delta t. So this says that if I know the expression for theta double dot, and I break this problem into small time steps, delta t, I can assume during that time step that theta double dot's constant, and I can use that to find theta dot. Now once I know theta dot, I can then calculate the new theta. So I can say theta dot equals delta theta over delta t, and that's going to be theta 2 minus theta 1 over delta t. And again, using the same idea, I get theta 2 equals theta 1 plus theta dot delta t. And then finally, I can use that to calculate lambda, right? So I can say lambda equals, going back up, I guess I could use this version up here. Lambda is going to be equal to, that was a 0. So lambda is going to be equal to mg cosine theta minus mr theta dot squared. Now I can calculate lambda, which is the force of constraint. Then I can repeat this for the next time interval and next, and I can get a plot of lambda as a function of theta, and then I can find out when lambda becomes 0, and that should be the same angle. Now to do that, I'm going to break this up into a whole bunch of tiny little problems. That means I'm going to do it in Python. So let's switch over to Python and finish this once for all, and then move on to better problems. So I'll see you over at Python. Okay, we're going to need a graph. So let's just go ahead and make a graph. So I'm going to say t graph equals object graph. I will try to, I've had a link on graphing before, but so let's just say I give it a title. X title equals theta in degrees. I think that you can do latex in the titles too. I can't remember. Y title is equal to, let's just say lambda. Lambda. Okay. F1 equals G curve. Color equals color.blue. So that first graph makes the axis with the labels and stuff, and the second F1 is the actual plot. Now I'm going to need my variables. Theta equals 0. Theta dot, I need to know that. Theta dot, got to spell it correctly, equals 0. I am going to need a mass and a radius, even though it doesn't really matter. M equals 1, R equals 1, G equals 9.8. Time step t equals 0, dt equals 0.001. Okay, I'm going to run this. Actually, let's just run it for a second. Okay, so because I want to run it for a second because it's just a little bit easier to make sure that it finishes. So I can say while t is less than 1, do the following. First thing I need to do is calculate the value for theta double dot. And I get that straight from my expression. So I say theta double dot, I'm going to call that dd dot equals g times sine of theta divided by r. Next thing I'm going to do is to use that theta double dot to calculate the new theta dot. So I'm going to say theta dot equals theta dot. I'm afraid I'm going to spell it. Plus theta double dot, dd dot, times dt. So again, in Python, this is not an algebraic equal sign. This is a make equal to sign. So it says take the old theta dot, add theta double dot times dt to it, and then make that the new theta dot. Now I can do the same thing for theta. And this is the Euler method. You can do more. A lot of people say, oh, you need to do Runge cut a fourth order. It's better. It is better, I agree, but I'm going for simplicity. Theta equals theta plus theta dot times dt. So now I've updated theta dot and theta. Now I can actually use my expression to solve for the normal force lambda. I'm going to call it the normal force. N equals m times g minus m times r times theta double dot. No, it's theta dot. I'm sorry, theta dot squared. And squared in Python is star star raised to the power. That's it. Now I'm going to plot that. F1 dot plot. I want the angle in degrees, theta times 180 divided by pi and n. And then I'm going to update time. T equals t plus dt. Let's save it. Circle thing 1 and run it. Oh, I do want to print. I do want to do this. Let's do this. T theta, theoretical theta. Let's just plot. Let's just say print other answer, other angle equals. It was the inverse cosine, a cosine of, it was 2/3 or 3/2. 2/3, yeah. And then that gives me the angle in radians, so I need to multiply that by times 180 divided by pi, and that will be in degrees. Okay, save it and run it again. I never ran it. Okay. Okay, I know what happened. So, so there's nothing here. And I'm glad that I ran it for a second, right? Because if I ran it while theta was less than, pi over 2, it would just run forever. The problem is that I started with a theta of 0 and a theta dot of 0. So it's at the top of that sphere and it's not moving. And you know what? It just stays there. So I need to give it a little tiny nudge or something. So let's put this at 0.001. I just picked a value. And now let's run it for a second again. Oh, I want to see what that printed down here. 48 degrees. Cosine is adjacent. Yeah, I thought it was 50 degrees. Okay, well that's fine. Run. Okay, so that looks good. The notice here, the normal force starts off at 9.8 because it had a mass of 1. So it's just sitting there on the top of the thing, not moving. The normal force would have to be equal to the weight. That's really a good sign. But it didn't run long enough, so let's run this for 3 seconds, and let's just see what happens. Okay, so over here, that didn't give it an angle, a time. I'm getting 58 seconds. Actually, I think that is the right answer. So let's run this as long as theta is less than 70. Let's try that. So while theta is less than 70 times pi divided by 180, run it. Oh, I didn't put a colon there. My fault, sorry. Okay, so now I have the force goes to 0 right here, right around there. Okay, let's get a better value, and that's different than this. I think 58 is the right answer. Print a cosine of 2/3. So that would be the angle in degrees. Hold on 1 second. I'm gonna get my paper. Okay, I have cosine. It's weird. Cosine of 2/3. That's really weird. Let's see. Let's just open a new tab. Let's just double check. I feel like I'm going crazy. Okay. A cosine 2/3 in degrees. 48. You can't take the arc cosine of 1. No, you can't do that. 2/3, 48. Why don't these two number things agree? Okay, let's go back over here to this thing. Let me do one other thing. What if I make the time interval smaller? And let's do this. I'm going to do this right here. Fast equals false. If I do that in the graph, it uses this plotly graph. So over here, see, it's just not doing it. So if I zoom in, I think I can just highlight that. Yeah. There, 0 is at 59 degrees. And that's 48. Why don't those two things agree? Well, I did this problem before. Okay, I guess I'll get back to this. Pausing here, and I'm going to figure out what's going on. Okay, I figured out my problem. It's just a dumb mistake, right? You can make dumb mistakes. So I just copied down the formula wrong. So in this part right here where I'm calculating the equation, I have the lambda, which is I'm calling n, is mg cosine theta minus mr theta dot squared. So I just didn't put in the times cosine theta. That's it. So now I run that. And now I go over here and let's highlight this thing down. And where is it cross 0? At 48.32. That's the same thing. Winning. Okay. You know, it was just a dumb error, but you got to track those errors down, and that's just the way things work. So, you know, there is a couple other ways to solve this problem. One way uses the x and y coordinates, which is kind of interesting. And I don't feel like I'm going to do that. I'm just kind of mad about that trick. So I'm going to do some other force of constraint problems that are more interesting, and that will be it for now.